Thank you, Ridmi. Let me get the slides started. I hope you can see my slides. Good morning or good afternoon, everyone, based on where you are. Yeah, as Ridmi said, my title is The New Frontiers in AI, Security and Privacy. I'm going to talk a bit about the dark side of machine learning and AI, not to scare everyone here away, but to create some awareness about what factors we need to consider when we are deploying real-time AI and machine learning systems. Right now, AI and ML is everywhere. In fact, it is the very reason why we all have gathered to this talk. The solutions have been exponentially growing in last decade, and any online activity we are doing today, behind any online activity, most likely there will be a couple of machine learning algorithms running. It can be recommendation systems, it can be voice recognition, or it can be even a simple spam detection. Photo tagging, face recognition, everything is run these days from machine learning algorithms. Why machine learning became so ubiquitous in the last decade? Two main reasons. First one is the availability of big data, and we learn how to process that data and how to manage that data, and the advances in GPUs. This took us out of what is called the AI winter, and from 2011 onwards, the last decade, so quite a lot of growth in machine learning and AI, and in some cases, the performance of AI actually surpassed human performance. Now, there are a couple of aspects of machine learning. Obviously, there are good applications, good use cases of machine learning. Self-driving cars are around the corner. We will probably see it in next few years. Machine learning and AI is used for medical diagnosis as well as drug discovery. It is heavily used in astronomy. And we also see all these cases where AI algorithms learn by themselves, for example, AlphaZero. All of these algorithms have the potential of creating quite a lot of social good. For example, machine learning is contributing well in the areas of assisted living. Equally, we hear quite a lot about the bad aspects of machine learning, the notorious parts of machine learning. Deep fakes are creating havoc in the internet. We are going to reach a point where it might be very difficult for us to decide a given image is true or fake. These days, generative adversarial networks or GANs have become really advanced, and they are generating photorealistic features. Equally, we have seen GANs being used to create nudes and all sort of antisocial things. This is one aspect. Also, we have seen machine learning and AI have been used to bypass security solutions. When Apple introduced Face ID a couple of years ago, it took only a few days for the attackers to generate the 3D model of a face using an AI algorithm, 3D print it, and bypass the Face ID security system. Equally, it's quite easy to build a model that now that can bypass the Google's reCAPTCHA system. That is the way you identify bots versus humans in the internet. This, you might have already experienced this. For example, you might have seen insanely difficult reCAPTCHA challenges, CAPTCHA challenges, when you try to log into a system. This is because it has become an arms race between the attackers and the defenders, and attackers are always finding ways to bypass or find loopholes in machine learning systems. Equally, there is an ugly aspect of machine learning. increasingly we are seeing evidence of algorithmic bias. We are seeing machine learning being used for unethical applications. For example, machine learning, the use of machine learning in recruitment has shown that the algorithms has some inherent bias. Now here you can argue this is happening because the underlying data is biased. But use of biased algorithms take this problem to a level we might not be able to handle in future. The scalability the machine learning model provides in these types of scenarios is scary. I'll explain one example where there was a bias in Apple's credit rating system. One time Apple introduced a credit rating system, credit card, and you can apply using your Apple ID. And it was found that if with the same income and almost the same background, Apple denies the credit card for the female applicant, whereas Apple is giving the credit card for the male applicant. The surprising, more horrifying fact was that the algorithm itself didn't have gender as an input, but the bias was somehow embedded in the algorithm. The bottom line is that it is about right time that we consider these aspects of machine learning: security, privacy, and ethics. I understand there is another lecture, or there was another keynote on ethics. So in this talk, I'm going to cover mostly the security and privacy aspects of machine learning. Now, security has quite a lot of cautionary tales to learn from. Most of the time, we rushed our products, we design things, and at the last minute, or even after the first attack only, we decide to fix security vulnerabilities. For example, we created the internet, we rushed to offer services over the internet. We had the 2000.com bubble. Still, we are trying to figure out how to make the internet fully secure. Telecom industry has quite a lot of examples where they considered security, or they didn't consider security in the design phase, and found themselves in quite a lot of trouble. For example, we learned in the hard way that security by obscurity doesn't work. For example, the famous 8 algorithm in GSM used in early 90s, to some extent, I think until early 2000s, was found to be secure only until someone tried to hack it. We also know that the implicit trust in most of the telco systems, that also doesn't work. It is something we should avoid. For example, the traditional SS7 signaling didn't have any sort of origin authentication, and it was easy to spoof messages or calls using that network. So what I'm trying to say is that it is about time that we make sure we have these security and privacy design requirements when we are building machine learning solutions from the early stages. Right now, where are we with machine learning? As I said earlier, the last decade was pretty much for getting things done, how to get things working. We made quite a lot of progress. We can handle quite a lot of big data sets, large data sets. We can build bigger models. For example, models like BERT has large number of parameters, take terabytes of input for training. Some are trained for weeks, months. And we also have built the infrastructure. Machine learning coding frameworks, TensorFlow, Keras, PyTorch, are already available, freely available, and there are high-level APIs as well. Some services provided by Amazon or even Google, services like AutoML. And now it's quite easy for anyone to build a machine learning solution. In fact, it will take only a few lines of code to build a simple image classifier. 10, 12-year-olds can do that. And right now, many businesses are leveraging this opportunity and are deploying machine learning solutions. But we need to take a step back and think about what are we doing. We are deploying models. Some of them are black box. So do we really know the limitations of these models? What kind of threats they might pose? For example, will it increase our attack surface? Can AI and ML used by the attackers to break into our systems? We need to think about how we are going to manage the risk. Are there any security and privacy risks in our machine learning models? If something goes wrong, it took what are we going to do? It took quite a lot of time for the industry to have the incident reporting in place. Now, most of the companies know what to do in case of a security incident. They usually have some managed service partner or some security company to call. They have the PR structure in place. So in case a reasonably technical company was hit by a ransomware attack, they know what to do. Now we are deploying machine learning solutions out in the wild. Real users are using them. We are making decisions about them. Do we know what to do if an incident happened in one of our machine learning systems? Equally, the ethical use of machine learning. Can the solutions we build be misused? For example, these days, there is a huge discussion going on face recognition. Some countries or some US states actually doesn't allow it. Inside Google, there are talks on Google being assisting to weaponize machine learning. So we have to figure out, are we doing the right thing? Or do the technologies we build contribute to some unethical usage? Okay. So next part of my talk, I'm going to walk you through with few scenarios on security and privacy of machine learning. In the first part, let's take what it means by security of machine learning. I will take what is called as adversarial examples as our use case, which is coming from a broader types of attacks called evasion. What adversarial examples do is something pretty simple. In the left-hand side of the screen, you see an image of a panda. Okay? If you feed this into an image classifier, it will be classified as a panda with some certainty. No drama there. Now, I'm going to manipulate some of the pixels of this image using the mask in the middle, and I'm going to get the resulting image on the right. For a human, it doesn't make, I can't see any difference. And probably you will not notice any difference as well. But if you feed the second image to a machine learning classifier, image classifier, it's going to classify this as a given with almost 100% confidence. Now, you might think this is something really innocent, yeah, cool example, nothing to do, nothing to worry about, which is not the case. Actual use cases of this can be really devastating. For example, researchers have demonstrated that this can be used to easily bypass face recognition systems. In the first example, you see an image of an famous actress. I have unfortunately forgotten the name, but you can draw a frame of a glass frame on top of an image, or even you can print it and wear it in real time. And you will be identified as Russell Crowe. Now, there are way too many examples where how to do these kinds of attacks. But the bottom line is that you can use adversarial examples to bypass face recognition system. Equally, This can have huge impact on autonomous driving. For example, someone can create an adversarial example to show a stop sign as a go sign, or no parking as a parking zone, where the car itself don't read the image incorrectly. And there are extensions. For example, some work has shown, like one in the top left, that by wearing a carefully printed pattern, person can completely bypass the CCTV camera face person detection system. Once you wear this printed pattern, the camera actually doesn't recognize a person there at all. Okay? These are called adversarial patches. You can leave them next to, for example, in the second one, next to a banana, and the banana suddenly become a toast. Pretty scary. Now, the adversarial examples are not only visible in images, they are visible in audio as well. Let me play you one single example coming from this site from Nicholas Carlini, one of the well-reputed researchers doing research in adversarial examples. So let me play two audios.
Without the dataset, the article is useless. Without the dataset, the article is useless.
What did you hear? You hear two versions saying without the dataset, the article is useless. But if you play these two audios to Google Home or a voice assistant, one will be translated by the Home Assistant as, okay, Google, browse to evil.com. Okay? And it was found that you can create as many messages like this as possible. Imagine someone create this video, some sort of audio, and play it as an advertisement in a TV. It will activate all the Google assistants in the world, for example. Equally, you can see adversarial examples in text. You can insert very carefully designed, identified sorry about that. You can insert some text to change the sentiment of the of a text. For example, in the above case, you say they talk about a film and you get a prediction of positive. You just insert one word footage. Immediately after that, the prediction becomes negative. So it's quite easy to manipulate even text. Most scaring part is that these perturbations are transferable and universal. You can design adversarial examples that can go through a couple of image recognition systems. Recent work called master phases actually showed that you need only around 7 to 9 phases, do some perturbations, and fool any commercial face recognition system. Unfortunate part is that right now it's an arms race. We don't have a defense. For example, in a recent in a conference in 2018, there were around 9 submissions proposing defenses for adversarial examples, and 7 of them were broken within a week. Literally, when the conference was running, these defenses were pointless. Okay? What we can do right now is we have to use a couple of techniques. We have to sanitize the input. We can do adversarial training. That is, we can train models, including adversarial examples. There are other techniques like defensive distillation and gradient masking. But most of them, we have to figure out on our own. For some problem, it might work. So some problems, it might not work. Adversarial examples are only a part of the problem. There are backdoors, data poisoning attacks, and model theft. For example, model is your IP. You use your training data, you build something, the model parameters are your IP. Somebody can actually steal them. What we can do with respect to adversarial examples and in general security, first thing is we have to admit that this is a problem. We have to do some risk analysis and see what are the risks we might be facing, and then see what kind of attacks we might try to defend in our model. Might be good practice to include security-related unit testing in your quality assurance process. And there are libraries appearing that might help you in this process. Clever Hans is one of them. Right. The privacy aspect, I will again walk you through one example and discuss the general ideas. In privacy, we try to reverse engineer models and find useful information. For example, some work have shown that if you build a face recognition system and deploy it as a machine learning as a service API, without any other information, the attacker can actually generate some of the faces, which is pretty scary. Okay. Equally, there can be such memorization attacks in NLP models. For example, usually when you build MLP models, it is supposed to complete some text for you. If you insert "what are you" to the model is usually give you the most likely next word, "what are you doing?" Now, if there is sensitive information in this training data, you can put a question like, what is Nicholas's social security number? And if the data is there, if it was there in the training data, it might actually pop out the number itself. And another type of attack is the attackers can try to figure out what type of data was used to train the model, whether the data was there in the training set or not. This is very critical if you are thinking about health applications, medical diagnosis applications. This might actually leak patient information. As imaginary as this sounds, attacker only needs some partial access to the training data set. They can train their own model and what is called as the shadow model, which predicts whether a given training sample is there in the training set or not. That is, on information leak is only one type of privacy threats related to machine learning. There are other attacks like radioactive data, and you can poison data when during training, etc. Now, similar to defending against adversarial examples, we are quite at the early stages of defending against information leaks. Membership inference, you can do it by plotting some graph like this before and after training. Also, you can artificially insert something called as canaries to quantify the memorization of the model. The idea is that you insert some canaries or very, very specific sentences during the model training and check whether the model has memorized. The general defenses, again, data sanitization. If you have critical privacy related information in your data set, you can remove them before you're training the language model. Part of the reason for memorization is the overfitting of the models. You can try to control it by using regularization, but now the technical solutions are also appearing. Technical solutions like differential privacy, you can use for, have a model that is more private. The idea of differential privacy is that it ensures that by participating or by giving your data to a model, it will not make you any harm. That is, your presence or absence of the model cannot be predicted by an attacker. So the idea is to use something called the differentially private stochastic gradient descent. I will not go into details. Where are we with the privacy? Again, we are at the very early stages. These days, only the new libraries are appearing. For example, TensorFlow has a framework for privacy. But in general, we can think about sanitizing data, do some regression test, and actually see whether our model is vulnerable to such attacks. The final part. Some of these problems can be solved by what is called, from a technique called as secure machine learning. The idea is we do machine learning on top of encrypted data. This problem comes from a very famous problem called the Yao's millionaire problem. Imagine there are two millionaires, A and B, and they want to figure out who is richer, but they don't want to share what is their wealth with the other party. So it turns out you could do it using a technique called secure multiparty computation. And after that, there are evolutions called homomorphic encryption and functional encryption that allows you to build models that can work on encrypted data. The idea is the client encrypts the data. Client is not trusting the service provider. So if you are providing a machine learning as a service, API, some clients may not trust you with their data. So the idea is clients send the encrypted data to you, and you apply your model multiplication, so all the mathematical operations on the encrypted data, and you get only an encrypted result. You don't know the result. You send the result to the client, and client can actually treat it. That's the idea of homomorphic encryption. Functional encryption is a lighter form of homomorphic encryption. It allows you to still work on encrypted data, but the model owner can get one specific functional evaluation in plain text. For example, this can be used in applications such as spam classification. So where are we with encrypted machine learning or secure machine learning? Again, in the early stages, but libraries are appearing. For example, TensorFlow has TensorFlow Encrypted. Also, we can think about using federated learning. I think this is also covered in some other keynote. But again, it's very, very early days. If you are using classical methods, you right now can implement solutions using homomorphic encryption. Some basic models like logistic regression can completely operate on encrypted data. So that brings me to the last slide for the conclusion of my talk. What's going to happen next? AI, the use of AI is going to get heavily scrutinized by governments as well as by attackers. Attacks are on the horizon. The fact that it didn't happen so far doesn't mean that it will not happen. We have to be on alert. If we are building data science solutions, we have to be prepared. Government regulation and legal frameworks are on the horizon. In fact, this year, the EU already initiated their discussions on Artificial Intelligence Act. They are going to give you guidelines on where AI can be used. If you are using, what are the things you need to consider? Public is being increasingly aware of AI bias and fairness. You have to be ready with incident response and public relations. If something goes wrong, you should know what to do. Also, finally, most likely in future, the regulation might say enforce certifiable models and defenses. That is, your model should have something like an ISO certification. This has this much of robustness, doesn't have bias. There may be some other auditing companies actually looking into your models. I think that's pretty much it. I'm happy to take any questions.